Welcome to Maths with EJD. In this video, we continue with system of differential equations, and in particular, the focus is on first order linear systems. And here we go. A first order linear system is a system of differential equations where each equation is of the first order. And by that, we mean that it involves derivatives, derivatives of the unknown function with respect to time or space, and linear in its unknown, linear in its unknown function and its derivatives. In essence, we are saying that the unknown function, the highest power of the unknown function is 1, and it is not multiplied with any of its derivatives and all that. So, with that in place, we can then talk about matrix representation. Let's talk about matrix representation of linear systems. Now, by now, you should know that matrices are really important because they help us do a lot of things. Okay, and that's why my very first playlist on this channel is on matrices. I have like, uh, I think, well, about over 20 videos or something. Matrix representation of linear systems. So, a general system of first order linear differential equations can be written as dy dt equals ay plus b. So you can see the dependent variable is y. So there's at no point do you see y being greater. Like the y here has power 1, and the derivative here is of degree 1 also because the power of the derivative is also 1. So here we are simply saying that y of t is a vector, of unknown functions, a vector of unknown functions. So that's all the y's, like y1, y2, and all the rest. Say y of t can actually be y1 of t, comma y2 of t. That's what that is about there. So you can have up to n, like we said in the previous video. Then here, A is a matrix. A is a matrix of coefficients, possibly. So the matrix is possibly a constant matrix, possibly constant or time dependent. It all depends. Okay. Then we have B. B is a vector. B is a vector of forcing terms. It's a vector of forcing terms. Okay. But it could be zero. Could be zero. If it's zero, right, that means the equation is homogeneous. If it's non-zero, that means the equation is non-homogeneous. I'll be looking at homogeneous and non-homogeneous linear systems in the next set of videos after this one. Okay. So let's take an example of what this can be. For example, the system, the x dt equals 3x plus 4y, and the y dt equals minus x plus y, can be represented as, can be represented as d dt of x of t, y of t equals 3, 4 minus 1, 1 into x of t, y of t. Okay, so as you can see, 3x plus 4y, 3x, 3, 4, then minus x plus y, that's minus 1, 1. So that's the matrix representation of that. So we can have that kind of representation going. All right, so at this point, let's look at another dimension to this. Say, let's go this way. Let's talk about existence and uniqueness theorem. Existence and uniqueness theorem for systems. So how do we know that a solution exists, and that if the solution exists, it's actually a unique one? That's what this statement is about. So the existence and uniqueness, the existence and uniqueness theorem guarantees the existence and uniqueness of a solution to a system of first order linear differential equations under certain conditions. Okay, specifically for the system dy dt equals ay plus b, that system we talked about before. Here we see that a of t and a of t, a of t and b of t are continuous functions. They are continuous functions of t in some interval, around t naught. In some interval around t naught. Okay. In this case, there is a unique solution. There's a unique solution to the system for any given initial condition. Of course, it is that initial condition that will guarantee that we go beyond general solution to particular solution, right? For any given initial condition, provided these conditions are met. These conditions are met. So the last thing we'll be talking about here, is it really the last? Yeah, I think so. Yeah, it's about the last thing here. I guess I also want to switch at this point to this. Let's talk about direction fields and qualitative behavior of solutions. Okay, So first of all, a direction field, a direction field, or what is called a slope field, a direction field or slope field, actually a graphical representation, provides a graphical representation of the solutions to a differential equation, okay, by showing the slope, or what you can call the derivative, by showing the slope or derivative of the solution at each point in the plane. Okay, so okay, I mean, well, good. So it shows uh the slope or derivative of the solution at each point in the plane. So let's check something about the qualitative behavior in this regard. Let me go this way. Qualitative, let me do it this way. Qualitative behavior refers refers to understanding, it refers to understanding the refers to understanding the long-term behavior, the long-term behavior of solutions without without solving the system, without solving the system explicitly. So without solving, you can have an idea of how the system is going to turn out in the long run. So this is typically done. This is typically done by analyzing analyzing the system's equilibrium points. You know, where I showed a bit of the idea of equilibrium points in the other video, in the first video on systems of differential equation, analyzing the system's equilibrium points and the nature of their stability and the nature of their stability. Okay, so let's look at an example now. Example. So the same system we talked about before, consider the system, the x, the t equals 3x plus 4y, and then the y dt equals minus x plus y, the same system we had talked about previously. So if we have the system, right, to find the equilibrium, right, to find the equilibrium points, to find the equilibrium points, you know what we just do? We know that dx dt is equal to 0 and dy dt is also equal to 0. So if that is the case, then it means that 3x plus 4y equals 0. All right. And then 3x plus 4y equals 0. Call that equation 1. Then we have minus x plus y equals 0. Call that equation 2. But I mean, it's glaring from here that minus x plus y equals 0 simply means that y is equal to x. So y and x are basically the same. So you can then slot that into equation 1. So call this 3 if you like. So put x for y in equation 1. And equation 1 we know is 3x plus 4y. 3x plus 4y equals 0. That means we have 3x plus 4x equals 0. And that is 7x equals 0. That simply means that x is equal to 0. And now that x is equal to 0, so we know that x is equal to y is equal to 0. So x is 0 and y is 0. So another way of representing that is just to say xy equals 0, 0, like this. So this is the result for the equilibrium points. So what we do next is to analyze the stability of this equilibrium by linearizing by linearizing around xy equals 0, 0. Okay. So in that case, the Jacobian matrix J of the system is, now see how this goes. Since you have the x, the t equals 3x plus 4y, you may want to call that big dx. I mean, just call it d, right? Yeah, just call it d, and then okay, maybe not d. Just call it like big X, so to speak, right? Or yeah, I think that's fine. Let's call it that. Or better still, let's call it x dot t. Maybe it is a better representation. X dot t. Okay. I mean the x dot actually, and then the y dt is equal to minus x plus y. Call that y dot. Okay. So we need that representation for the Jacobian. So the Jacobian of the system is not this now. This is not the Jacobian of the system. The Jacobian of the system is actually the J I'm going to write out now. So that is actually J. So that would be J of x comma y. And that is equal to this. This is how this should look. You can see the Jacobian as partial derivatives of x and x dot and y dot with respect to x and y. So here it's going to be partial x dot, partial x. Then here it's partial x dot, partial y. Then partial y dot, partial x, and partial y dot, partial y, like this. So that's what the Jacobian should look like. So we have j of x comma y to be equal to, so differentiate 3x, x dot, x dot is 3x plus y. 3x with respect to x is 3. I mean 3x plus 4y, differentiate with respect to x, that's 3. 3x plus 4y with respect to y, that's 4 here. It's more or less like just writing out the coefficients. But for y dot now, minus x plus y, differentiate with respect to x, you get minus 1. With respect to y, you get 1. So it's more or less like just writing out the coefficients of what you have on the right-hand side, okay? So, and from our knowledge of matrices, we can get the determinant of, so we now need the determinant of J minus lambda I, because we are looking for what we call eigenvalues. So I can say to find eigenvalues, I did a lot of work on this under the matrices playlist. You want to check that out. So determinant of j dot I mean j minus lambda I is equal to 0. So that simply means that you are looking for that's the same thing as, I like to write my determinant this way. So that's determinant of j minus lambda I. J is already 3, 4 minus 1, 1. So minus lambda I, that's a unit matrix multiplied by lambda. So that's 3 minus lambda 4, then minus 1, 1 minus lambda. All of this should be equal to 0. So if we take the determinant, so that's like this multiplied by this, that's 3 minus lambda into 1 minus lambda minus, then 4 minus this. Now that's, let me do it this way. That's minus this. Now that's minus 1 times 4. And all of this is equal to 0. So if you expand this now, 3 times 1 is 3. 3 times minus lambda, that's minus 3 lambda. Minus 4 lambda times 1, that's minus lambda plus lambda squared. Minus and minus is plus, so we have plus 4 here equals 0. So this is the kind of thing we have. So that means that lambda squared, right? Lambda squared, right? Minus 4 lambda plus 7 is equal to 0. Okay? So this is, if you remember, this is what we call the characteristic equation. Characteristic equation. So if we solve the characteristic equation, we get the eigenvalues. So that's what led us here, right? So, we can use the quadratic formula. Using the quadratic formula, so we want to find the eigenvalues, which will tell us the stability. Using the quadratic formula, so we know that simply lambda is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. That's comparing it with standard equation. So, lambda squared minus 4 lambda plus 7 equals 0 simply tells us that a is equal to 1, the coefficient of lambda squared. That's 1. Then b is equal to minus 4. That's this now. Then c is equal to 7. Okay, so with that in place, we can then go for lambda itself, which is equal to minus 4 plus or minus square root of b squared, that's minus 4 squared, minus 4 into 1 into 7, all over 2 times a, that's 2 times 1, so that lambda is equal to 4 plus or minus square root of 4 squared is 16, 4 times 7 is 28, all over 2 times 1, 2. So we have lambda to be 4 plus or minus square root of 16 minus 28 is minus 12, I think. Yeah. Yeah, minus 12 all over 2 right here. And then we have, hope that's correct. 16 minus 28 is minus 12. Yeah. 12 plus 16 is 28, I believe. Yeah. Okay. So yeah, that goes. So we have lambda is equal to 4 plus or minus. Now, square root of minus is complex, so complex 12 all over 2. And that means that lambda is equal to 4 plus or minus I. 4 times 3 is 12, right? So so that we have square root of 4 times 3 all over 2 now. So lambda is equal to 4 plus or minus I. Square root of 4 is 2. So we have 2 root 3 divided by 2. If that is okay, I hope I got that right. So 4 squared is 16. 4 times 7 is 28. Yeah, that works. Yep, 4ac. 4ac. Okay, minus b squared. Right. Okay, I think that's it. So we now have lambda is equal to divide through by 2. So we simply have 2 plus or minus 2 plus or minus I root 3. Okay, so this automatically tells us that we have a complex root and that is oscillatory in nature. Okay, so we can say this now that in conclusion, the equilibrium point, the equilibrium point is unstable. How do we know that it is unstable? It is unstable because it's unstable. Let me put it in brackets. It is unstable because the because the real part of lambda, the real part of lambda is equal to 2, and that is greater than 0. That makes for stability. So if it is less than 0, it would have been that makes for instability. But if it was less than 0, it would have been stable, right? That's one aspect of it. So it is unstable then, and solutions solutions will spiral away, and solution will spiral away from the origin, from the origin. Okay, so it will spiral away from the origin. Why? Because the root is complex, because the root is complex. Okay, that's the reason why it will spiral away from the origin. So it's some kind of oscillation getting out of the origin because it's unstable, right? Okay, so and this will be done in a manner. This will go in a manner. This will go in a manner determined by the eigenvalues, by the eigenvalues. So for sure, we have two eigenvalues now. So we have 2 plus I, we have 2 plus I root 3, and we have 2 minus I root 3. Those are the two eigenvalues now. So in either case, the real part is greater than 0, and that means that calls for instability. And once it's complex like that, because it's unstable, so you're going to be having something like this. So it's more like I just want to do something. Let's say you have this now. So it means because it is unstable now, you have something going out of the origin. So it's spiraling out. So that's the, because it's not stable. But of course, to get a better picture of what I mean here, um, Python to the rescue as usual. So you have this in Python code 3x plus, so you can see in lines 8 and 9, we have the x dt 3x plus 4y, the y dt is minus x plus y, and then you write all the other things. So you can study this. I'm going to put this on Facebook as usual, so you can follow this through later. So I just want to run it to show you the direction like we've been talking about. So now you can see that it's more like it's spiraling out of a particular point because of the instability. And the spiral nature is due to the fact that the solution is complex. So you see the eigenvalues of the system is what you have. It's 2 plus root 3 now 1.732j. That's the complex. That's that for one part. The other part is 2 minus 1.732, just like what we exactly got, which actually works pretty well, because what we have is you know 2 plus 2 plus or minus I root 3, and root 3 is 1.732. So with this and the Python, so we have justice done to the whole concept of direction fields and qualitative behavior solution. So we can have an idea of what is going to happen to a system by just knowing the eigenvalues, by knowing the eigenvalues like this. All right, so with that, we come to the end of this particular video. You want to sit with it and really understand, because we have more things coming. From the next video, I think we'll be talking about linear homogeneous systems. And after that, we'll be talking about non-homogeneous linear systems also. So watch out for that. Feel free to tell me in the comment section how helpful these videos are for you. And let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. If you have not subscribed to this channel, please go ahead and do that. If you have subscribed or you're just going to subscribe now, be sure to hit the notification bell also, so you can always get alerted each time a new video is released. Don't forget also to to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Okay? Bye.